Okay, so welcome everybody. It's our last week, and the plan for today is to finish the discussion on Noetherian modules and rings, and then go on to explain the primary decomposition. So, okay, there is this concept of Noetherianity, which was introduced by Emmy Noether, is some finiteness condition. So maybe I recall it very briefly. So M is an A module. And it's called Noetherian. So it's an adjective. Well, there are several equivalent definitions, but one possibility is to say that every submodule is finally generated. Every submodule, say N of M, is finally generated. Okay, and then we investigated this concept. It was not very difficult. Then, for instance, we showed that homomorphic images of Noetherian modules are Noetherian. By definition, every submodule of a Noetherian module is Noetherian, and so forth. And then we looked at this notion for rings. So when is a ring Noetherian? Noetherian. Now this means that it is Noetherian as an A module, but more explicitly, this means that every ideal of the ring is finally generated. Every ideal of A is finally generated. Okay, so for instance, we showed that polynomial rings in several variables over a field are Noetherian. Okay, we proved that in the chapter on Gröbner basis. Also here, it's interesting to know how this property is inherited. So for instance, what we showed, homomorphic images of Noetherian rings are Noetherian. So for instance, I can write it this way. So if the ring, if A is Noetherian, and A is an ideal, of course, it's finally generated, then it's very easy to see that the factor ring is Noetherian. I think that was the last thing that we proved. So really one has to be a bit careful. So it's not true that subrings of Noetherian rings are Noetherian. So this is in general wrong. So for instance, you can take, okay, silly example. So I can write warning, maybe warning. Subrings of Noetherian rings may not be Noetherian. Okay, may not be Noetherian. Okay, and one silly example is just this. You take, I take here a polynomial ring over a field in countably many variables. So this is not Noetherian. You can have a, okay, you can have an infinite, strictly ascending chain of ideals. You just take the ideal generated by the first I variables. So this is not Noetherian. It's not Noetherian. Okay, not Noetherian, but now just embedded into its quotient field. Okay, but it is contained in its quotient field with just a field of rational functions. And of course, every field is Noetherian because it's a field. As field. Okay, so you see. Anyway, this is a very general principle. You can take any non-Noetherian integral domain, it's contained in its field of fractions. Okay, so this was a warning, but now, but what happens with localizations? There, the situation is very nice. Let's briefly discuss this. That's also very simple. That's in Atiyah-MacDonald. This is the proposition 7.3, which says that if you have a Noetherian ring and you localize, then you again have a Noetherian ring. So if A is Noetherian, okay, I hope you can read it. S is a multiplicatively closed subset. Okay, then we form the localization, and this is Noetherian. The proof is very simple. So we know how the ideals in the localization look like. So ideals in the localization have the form. Okay, I can write it this way, s to the minus 1a, where a is an ideal of S. And I hope this notation, okay, you remember it, it explains itself. You just take you take an element of the ideal A and divide it by any denominator S. Now you see if, okay, let's say if A is generated by x1 up to xr, then immediately clear that s to the minus 1 is generated by these elements. You just interpret generators xi as elements of the localization, and the rest is clear. So this is a real trivial argument. So in particular, okay, let me write it for the sake of completeness. Corollary, if A is an Noetherian ring, and you have a prime ideal, okay, I can write it this way, a prime ideal, then I form the localization, the local ring, AP, okay, is Noetherian. Okay, this is important. Okay, a local Noetherian ring. Okay, so what is the most important result when we deal with this concept? This is the Hilbert basis theorem. This is the theorem 7.5 in Mattia MacDonald, Hilbert basis theorem. Basis theorem. What does it say? I mean, I don't think Hilbert did state it that way, but the most elegant, the general way to say it is this. If A is a Noetherian ring, then the polynomial ring in one variable over A is Noetherian. Polynomial ring AX is Noetherian. Okay, and let me immediately write as a corollary. The corollary immediately tells us what happens if we have several variables. This is in Mattia MacDonald corollary 7.6. So if A is Noetherian, then you can just repeatedly apply this Hilbert basis theorem. You join one indeterminate after the other, and then you see that the polynomial ring in several variables is Noetherian. Okay. Now, as it happens, I prove this corollary when A is a field. So prove this, prove corollary if A is a field. A is a field. Okay. So I'm short of time. Also, it would be a bit boring. So I'm going to skip the proof. So I skip the proof. Not that the proof is difficult. I mean, basically I did the proof when I did it for fields, and the proof in general is it's almost the same. So I skip this proof, and then, but we have the important special case. Okay, so questions on that? No questions. Okay, very good. Then one corollary here that is quite useful. Maybe put it here. Okay, it gives us many Noetherian rings. So it says the following. Okay, let's assume B is a finally generated A algebra. Let this be a finally generated A algebra. So we know what is A algebra. It's a ring B together with a ring homomorphism from A to B. Now I assume B is finally generated A algebra, and I assume that A is Noetherian. So if A is Noetherian, then B must be Noetherian as well. If A is Noetherian, then B is Noetherian. Ring. Okay. Okay, maybe I should write ring. Okay, otherwise it may be Noetherian ring. Then follows B is Noetherian ring. Okay, so what is the proof? Well, it's very simple. We just apply this Hilbert basis theorem. So let's assume B is generated over A by elements small x up to xn. Okay, but then I have what I can do. I can form the polynomial ring over A in the indeterminants x1 up to xn. Now these are variables. Okay, and I have a surjective ring homomorphism. So this just maps capital Xi to Xi. This is a surjective ring morphism. And now the Hilbert basis theorem, okay, it had a number. It was theorem 7.5, gives me that this polynomial ring is Noetherian. Okay, and then I just use that homomorphic images of Noetherian rings are Noetherian, and I'm done. Okay, what was the other? Apply. Okay, of course I don't know these numbers by heart, but it was proposition 7.1. Okay. So there are maybe two cases that are of special interest where this corollary applies, or I can say in particular, okay, every finally generated ring is Noetherian. Finally generated ring is Noetherian. Because a ring, I mean, is an algebra over the integers. The integers, they form a Noetherian ring. And the other situation of interest is every finally generated algebra over a field is Noetherian. Every finally generated algebra over a field is Noetherian. So maybe one difficulty here is one has to really tell apart modules and rings. And when I say generate, you always have to think in what sense, as a module, as a ring, right? So one has to distinguish this. But once you manage to distinguish this, I don't think this is a difficult concept. So there was, I mean, in this chapter, there was no difficult proof, I believe. So are there questions on that? No questions. So by the way, in most textbooks and so, I mean, this concept of Noetherian is introduced much earlier. On the other hand, I quite like Attila MacDonald, he introduced this only, towards the end. And this also shows that, I mean, most of the things you do don't require this hypothesis. Okay, most of the things, tensor product, localization, etc., etc. You don't need to assume that your modules are finally generated. Okay, but now we will enter a new chapter, and it's where we need this. Now, this is the last chapter, unfortunately, of the lecture. There is no time for dimension theory, which is actually probably the pinnacle and highlight of all of the theories. So what I used up too much time with Gröbner basis. So this is primary decomposition. Last chapter, primary decomposition. Okay, so that's by itself a quite important result. In that generality, going back to Emil Noether. So if you think of numbers, okay, think of the ring of integers, then we have the notion of the prime number, and we know every integer can be written as a product of prime numbers, and we know it's essentially unique. But the question here is whether one can have such a decomposition, you know, for other rings. Okay, and it turns out for Noetherian rings, there is such a decomposition. It's the primary decomposition. Okay, one problem with this is not completely unique. So with respect to certain aspects, the decomposition is unique, with respect to others not. So it's a bit more subtle, okay? It's actually quite subtle, the primary decomposition. But certain aspects of it are relatively easy to understand. Okay, so the first thing is, I mean, what will we do? If I have a ring, instead of the notion of the prime number, I already defined the notion of the prime ideal. Okay, so, but this is not enough. So, okay, if you think of numbers, you can say every integer is a product of prime powers. And actually what we need to do, we need to find the appropriate generalization of the notion of prime power. But this prime power analog will not be a power of a prime ideal. It's something more general that we call primary ideal. Okay. So, and let me define what is a primary ideal. So this is the key definition. So definition. Okay. An ideal, I will always call it Q in a ring A, is called primary I apologize, we have constructions going on, so maybe you can hear it. So if, well, we don't want Q to be the whole ring, okay, boring condition. And now comes a condition that is a bit weaker than the definition of prime ideals. So let me write it down. For all x, y in A, let's assume x times y lies in Q, okay? So in the definition of a prime ideal, then I would say, then either x is in Q or y is in Q. But here, now I say it a little weaker. Let's just say, okay, and it's a bit cleaner. Let's assume x is not in Q. Then I cannot say that y will be in Q, but what I can say, y will be in the radical of Q. So this is the radical. So actually now I realize I should recall some facts about radical. I will do it in a moment, okay? In the radical. So that's the definition, radical. Or I can say, or it means, okay, Q primary. If I go to factor ring, I can express it this way. I take this factor ring. It should not be the zero ring. And this condition here, so you go to the, okay, you apply canonical homomorphism, then what you have? You have like x bar times y bar equals 0, but x bar is non-zero. Okay, this means if you have such a situation, it means your y bar is a zero divisor. Okay, you can multiply it with a non-zero element, but you get 0. And this condition, what does it mean? Y in the radical, I mean, if you look at y bar, it means, okay, what does it mean in the radical? It means some power of y lies in Q. So it means some power of y bar is 0. Okay, so it would mean y bar is a nilpotent element. So this condition means, okay, I over Q non-zero, and every zero divisor of the factoring is nilpotent, and every zero divisor of A mod Q is nilpotent. Okay, so does it mean? Okay, so maybe it's a good idea before I continue to recall a little bit what was the radical. Okay, I made a note. Okay, recall radical of an ideal. Okay, some people also write it with the square root, but doesn't really matter. So maybe the radical, let me define it again, consists of those x in A such that some power, there's some m in n, such that x to the m is in A. That was the radical. Okay, so if A is 0, this is just the set of nilpotent elements. So this is an ideal. And what we also, I mean, this next property that I write is really trivial, but I will use it all the time. So if you think of taking R as some operator, so it respects monotonicity, so this is trivial, but it's useful. And the other property that I will use all the time is this. So if I take the radical of an intersection of ideals, it's the intersection of the radicals. And that's also obvious to prove, but this is useful, okay? So, okay. So, okay. So let's discuss a little bit this concept of primary ideals. So I have a remark. The first is quite clear. It says every prime ideal is primary. This I already explained. Is primary. Okay. Second remark is that inverse images of primary ideals are primary. So if I have a ring homomorphism, okay, Q is a primary ideal of B, Q primary of B, then inverse image is a primary ideal of A. So this is really trivial to verify. I leave it to you. Okay, trivial to verify. Okay, so let's investigate these primary ideas. There are some subtleties here. It's not a concept that is too easy to understand, I think. Okay. Okay. Proposition. By the way, I think this primary decomposition was first, I mean, the definition of the concept, I believe, and also the primary decomposition for polynomial ideas is not due to Emmy Noether, but to Steinitz, who was a mathematician, but he was also a chess world champion. I think he has the record for being world champion in chess for the longest time, and that was actually his profession. I mean, he got a PhD in mathematics, but then he lived from chess. Okay, and then Emmy Noether, I mean, she took the result by Steinitz, generalized it to any Noetherian rings, and the proof became much simpler. The proof by Steinitz was complicated. Okay, so just the annex thoughts. So what I can say, if I have a primary ideal and I take its radical, then this always will be a prime ideal. Okay, it's like the prime ideal belonging to the primary ideal. Let Q be a primary ideal of A. Then the radical, yeah, that's the smallest prime ideal containing Q is the smallest. Prime ideal containing Q. Okay, it's a prime ideal and the smallest one containing Q. Okay, let's prove this. That's pretty simple. Let's first check that it is, let's first check that the radical is prime. Okay, that's a claim. Let's check it. So, okay, so I take a product X and Y that is in the radical. I have to show X or Y are in the radical. Okay, so by definition, this means there is some non-negative integer n such that x to the m times y to the m is in Q. Okay, now I use that Q as a prime ideal. So I can say either, maybe I write it here, either x to the m in Q or y to the m in Q. And of course, this means either x in the radical of Q or y in the radical of Q. Okay, so this clearly shows that the radical is a prime ideal. That was pretty trivial. Okay, and now second statement is the radical is the smallest prime ideal containing Q, but that's also very simple. So if, let's assume, okay, if P is a prime ideal, if P prime, and it contains Q, okay, like that, then I take radicals, okay? Taking radicals is monotonous. The radical of a prime ideal is itself. So what I see, the radical of Q must be in P. So therefore, RQ is the smallest. Is the smallest. Okay, blah, blah, blah. Smallest prime ideal containing Q. Okay, I proved the proposition. Is there a question on that?
Yes, actually.
Yes. Mm-hmm.
In the
Okay.
first part, it seems like you used that Q as prime, right? But it's only primary, where you wrote x to the m times y to the m is in Q, and there follows either x and x to the m in Q or y to the m in Q.
Okay, my proof was not good, but I can correct. Thank you very much for pointing this out. But I can correct it with, okay, let me do it in yellow. Okay, sorry for that. Now, okay, okay, you are perfectly right. I was not concentrated. Now this implication, here I use that Q is primary. So x to the m is in Q, or the other guy is in the radical of Q. Okay, but if y to the m is in the radical of Q, it means y is in the radical of Q. Okay, right? So there are two things. I mean, that was not correct. Well, it was correct, but it was misleading. But this implication, y to the m in the radical means some power of y to the m is in Q. So therefore, some power of y is in the Q. Okay, is it clear now?
Yes, thank you.
Okay, but yeah, this was not very good. Thank you. Okay, always good to ask for questions in case there are such these little accidents. Okay. So now we see, so whenever I have a primary ideal, I can associate with it a prime ideal, namely the radical. So now, okay, there is some notation. So if P is the radical of Q, then Q is primary, then we say Q is P primary. If this Q is primary, then say Q is P primary. Okay, so this is a naming I will use in the following, P primary. Okay, that's kind of where it belongs. So let's do some examples. First, the integers, like our mother ring. Okay, so what are the primary ideals there? What do you think?
The principal ideals generated by powers of primes?
Correct. Yes, and zero.
Yeah.
Okay, zero, of course, zero. Maybe I can write it this way. And right? Powers, okay. Ideals power, then by powers of primes, where P prime and the natural number. Okay, should be positive, otherwise, okay, we don't want the whole thing to be very easy to check. Okay, but now I give you an example that shows that it's not always like that, that the primary ideals are powers of prime ideals. So life is more complicated. So this we can already see if we take the polynomial ring in two variables over a field. If you take it in one variable over a field, it's like the integers. Okay, we don't see it, but with two variables, it already happens. So let's take this Q. This is like the standard example. It's in every textbook. It's the ideal generated by X and Y squared. Okay, now I claim this is primary. Okay, so why is it primary? Let's look at the factor ring. So, okay, if I divide out the X, what I get is this ring, which is isomorphic to this ring. Okay, and here let's check that every zero divisor is nilpotent. So this has zero divisors. So these are the elements that don't have constant term, has the multiples of y, okay, lambda and k. So I mean, if you square it, you get 0 because y squared is 0. Okay, and they are all nilpotent, which are all, which I just said, they are all nilpotent. Okay, so what I see, indeed, Q is primary. And what is the radical? Well, the radical, let's call it P. This is, I mean, very easy. It's the radical, it's the ideal generated by X and Y. So it's the maximal ideal, okay, describing the origin. Then what do we have? So, okay, I claim P square is contained in Q, is contained in P. Q in P is clear. What is P square? Right, so P, maybe right, P square is the ideal generated by X square, X, Y, and Y square. And this is contained in Q, okay? But in, well, but it's strict. Okay, so this shows that Q is not a primer of a Q is not power of a prime ideal. If it were a power of a prime ideal, that prime ideal had to be the radical. Okay, but here we see is not true. Okay, so primary ideals are not just powers of primes. So I have another warning, but I will not detail it, but I just want to say it. Warning. Okay, you can maybe try the other. So now we have seen an example of a primary ideal, which is not a prime power. But you may hope that whenever you take a power of a prime ideal, it will be primary, but that's also false. So a prime power, P to the n, where P prime ideal, where P prime ideal is not necessarily primary. Necessarily primary. Okay, so I'm a bit short of time, so I skip. One can give examples, so let me skip that because I'm running out of time. But there are such examples. So but the situation becomes much simpler in a way, nicer in a little bit special situation, namely when this prime ideal that which is the radical of the primary ideal, when this is maximal. Okay, then the situation is quite clean. Let's focus on that. So it says, okay, the next proposition says, if I have an ideal A and the radical is maximal, okay, then this is enough to conclude that A is primary. Okay, so that's useful. So in particular, okay, if I have a maximal ideal, if M is a maximal ideal of my ring, then all its powers are primary. All powers M to the I, let's say, I in N. Okay, I shouldn't. Okay, all its powers are primary. Of course, I should not be 0, otherwise I get the whole thing. Okay, so this is nice. Powers, okay, I have a power of a maximal ideal. Okay, the radical of this guy is just M. Okay, then apply the proposition. I see M to the I is primary. So this is something to remember. Okay, so let's prove that. Good. Okay. Okay, let's say M is the radical of A. Okay. So I assume this is maximal. This is a maximal ideal. Okay, so then this is maximal. Then M is the only prime ideal containing A. Okay, then let me check that. Okay, maybe I go in step. So the statement is this. Let's put it maybe as little claim and then show it. Claim M is the only prime ideal containing A. So let's check this. So okay, if I have a prime ideal P which contains A, and then I do my usual trick, I go to the radical. Okay. The radical of A, this is my M, and this is assumed to be maximal. This is my assumption. It's a maximal ideal. And the radical of P, of course, is P. So what I see, M must be P. Okay. So I showed my claim. Okay, now let's go to the factor ring. So it follows that, okay, M bar is the only prime ideal of the factor ring, A bar. Okay, it's just a reformulation of my claim. M bar is the only prime ideal of the factor ring. Okay, so only one prime ideal, so it must be a local ring. Okay, local ring. Okay, so local ring. And what do we need to show? We want to show that every zero divisor is nilpotent. Okay, but every zero divisor, let's say X bar of A bar, must be in M. Okay, must be in M bar. Otherwise, it would be a unit. Okay, must be in M bar. So this means if I turn it around, X is in M. Okay, the X that represents the element. Okay, and then M was defined as the radical of A. So there is some natural number N such that X to the N is in A. That was the definition of M because of the radical of A. Okay, so maybe it looks like I'm going around, but if I write again bar, X to the N bar is 0. So X bar is nilpotent. So I showed that indeed A is primary. read it. Questions?
How exactly does the second claim follow from this?
Which is the second?
That if M is a maximal ideal, then its powers are M primary.
Okay, this is the following. Okay, let me here. Good. So I look at this ideal, but maybe I can write it in yellow. If I take the radical of this, I get M. So now I have the M to the I is my ideal A, and its radical is maximal. And then I apply part 1.
Okay. Yeah, okay.
Okay.
Thank you.
So I didn't write, I said it, I think, but I didn't write it. Okay. Good. Okay. So now we are moving towards primary decomposition. Then I have a little lemma here that will be very easy. It says, okay, let's say we have a couple of primary ideals, but they belong to the same prime. So let's say Q1 up to QR, they are all P primary. So they have the same radical. Then what I can do, if I consider the intersection of those, then right, this is also P primary. Then this is P primary. So it will be a primary ideal, and the radical is also P. So proof, let's see. First thing is, I mean, like the first statement is we check what is the radical. Maybe this should be called Q. Let's call this Q. The radical of Q is the intersection of the radicals. Okay, this is our principle that I recalled. Okay, this is in P intersected with P, with intersected with P, this is just P. Okay, so, right. So if this Q is indeed primary, it must be P primary. But now let's check that Q is primary. Okay, then by definition, what we have to look at, I have a product, X, Y, it's in Q, and let's say X is not in Q. I need to show Y is in the radical of Q. Okay. So if X is not in Q, okay, then there is some index I, so that X is not in QI. Okay, Q is the intersection of the QI. Okay, now I use that QI is primary. Okay, now from, okay, X, Y is in Q. So in particular, it's in QI. But I know Q is not in QI. Now I use QI is primary, and I see that Y is in the radical of QI. So here I used QI is primary, but the radical of QI is the P. And this is the radical of Q. So I showed that indeed Q is primary. Okay. Questions? No question. Good. So now it's easy to guess what will be a primary decomposition of an ideal. Well, oh no, it's not easy to guess. There are like, what are the options? If you think of prime numbers, you would think of product, but it turns out to be the product of ideals is not such a nice notion than the intersection. So you think of intersection. So primary decomposition of an ideal will be, okay, a way to write the ideal as an finite intersection of primary ideals. Okay, so that's the definition. A primary decomposition maybe put it in yellow. Primary decomposition. Oh, this should be yellow, sorry. Of an ideal. A of my ring is, maybe I say is an expression, okay? You are not pedantic, okay? I write it as an intersection of finitely many, say n many, and the Qi are primary ideals. Okay. So we will, in a moment, we will prove that for an Noetherian ring, primary decompositions exist. Okay, always. Okay, but the question, I mean, is how about uniqueness? And if we look at this definition, it's already clear it cannot be unique. Okay, but we can, okay, require a little bit more. So maybe we have hope of uniqueness. So what we can do, so by this lemma, I just proved, what was it, the lemma? Okay, the lemma, maybe, sorry, this is for free in a TM McDonald's. Maybe I should put the number, yes. So let's assume I have such a primary decomposition. Okay. And then I just look at the radicals of these QIs. Let's call them PI. PI are prime ideals. Okay. But these prime ideals may not be distinct. Let's say you have a decomposition, say the first three have the same prime ideal. But then you can just combine these three primary ideals into one. And because of the lemma 4-3, the intersection of the first three primary ideals will again be primary. They belong to the same prime ideal. Okay, so by doing this, we can, okay, then assume that in a primary decomposition, the corresponding prime ideals are pairwise distinct. So maybe let me write it. My lemma 4-3, we may assume. Okay, that the PI, which I define as the radicals of QI, are pairwise distinct. Okay. Okay, the idea is group together QI, the QI with the same radical. Okay, good. So this is, we assume this, but then still it may be, you may have such a decomposition and it may be that you can leave out some parts. So maybe you can leave out QN, it's not necessary. So you don't want to have this redundancy. So we also, we assume, okay, that you cannot leave out anything. So I can write it this way. We assume, let's say I have the intersection of the QJ where J different from I. Okay, do I want to write it this way? Okay, I want to assume that this is not in QI for all I. Because if it were in QI, I could just leave out the QI. Would be necessary. Okay, there is no point in writing intersect with QI if what you have is already contained in QI. Okay, so means okay, none of the QI can be left out in the decomposition. Okay, some people say it's irredundant. Okay, so we call such a primary decomposition satisfying these two properties. On the one hand, pairwise distinct, and on the other hand, this, we call those primary. Call such a minimal, call such primary decompositions minimal. Minimal. Okay, minimal. Okay. Right, okay. So let's first show the existence, okay? What are the questions to? No question, I think. Okay, now there is this theorem due to Emmy Noether, 713 in ATM McDonald. Okay, maybe I can write Noether. Okay, in an Noetherian ring, okay, every ideal has a primary decomposition. Okay. Right. So as you will see, the proof is not a difficult one. It's short and elegant. So, but I think Emmy Noether, she got quite well known with this because she managed to identify this property of rings, which we nowadays call Noetherian. When you assume this, you can do many, many things that people maybe, have they kind of like in the polynomial ring, things were proven in much more complicated ways. And this is exactly the property that we need. So let's do this proof, okay? The proof goes in 2 steps. So in the first step, let's introduce an auxiliary notion. Okay. We call an ideal irreducible, A, irreducible, okay, if, well, what is the point? I want to decompose it with respect to intersection, okay, but it should not possible to do this anymore in a non-trivial way. So whenever I write A as an intersection of 2 ideals B and C, then A should be B or A should be C. Okay, so it means I cannot further decompose in a non-trivial way. This is the meaning of irreducible. And then the first lemma, this is lemma 711. It says that in a Noetherian ring, every ideal is a finite intersection of irreducible ideals. Ring, every ideal is an intersection. My pencil reacts a bit strange. Is an intersection or is of finitely many irreducible ideals. Okay, so we prove this, and in the next step we will prove an irreducible ideal is primary, and then we are done. Okay, that's the plan. Okay, let's first do the lemma. So this is pretty straightforward nowadays, Noetherian induction. Let me not write it too formally, I just explain you the idea. Okay, so given ideal A. Okay, so if it is not irreducible, so I don't want to do an induction proof. I always think it's a bit, it's not necessary to explain. If A is not irreducible, so then I have a decomposition, a non-trivial decomposition. I write it as say A10 intersected A11. And both ideals are strictly larger than A. So the A10 is strictly larger than the A11. Okay, that's what it means not to be irreducible. So I can do that. But then I just continue, and you see let's maybe look at the first one. If A10 is not irreducible, okay, then I have, okay, I can go on. I will have a decomposition. Now it's just a question of the notation. So A10, maybe I write it as A2. I don't know. Don't pay a lot of attention to my choice of indices. I don't remember why I wrote it this way. 102223. Okay. Also properly contained. Okay. And right. And then I go on. Then I go on. So say similarly, if let's say if A20 is not irreducible. Okay, so why do I? Okay, sorry. Okay, maybe this should be 0. Now I understand. I could not read my letters. This should be 20 and 21. I understand. Sorry about that. Okay, makes a lot of sense. 2021. So okay, right. You see, if these two guys, if they are irreducible, then I stop. But if not, then I can go on. So if they are not irreducible, then I just go on, etc., etc. Then, right. Okay, maybe I don't have to write everything. I mean, maybe let me rather put a picture. Okay, I want to explain in terms of a tree. So I have my A. So I found the decomposition. So here I had A11 and here I had A12. Okay, then I decompose. If they are irreducible, I stop. But if not, I will decompose. Okay, let's assume maybe this guy was irreducible, then I stop. Okay, but then I compose this. Or maybe I go with this. Maybe this was irreducible, then I'm here and so on, etc. Now, I mean, what we want to prove is that this procedure somehow stops after finally many steps. Okay, then we would be done. But if it would not stop, what would we get? We would get an infinite, strictly decreasing, strictly ascending chain of ideals. Okay, so let's say, maybe, I don't know, we have this and this and this and this, and let's say it never stops. Okay, this would contradict the property that the ring is Noetherian, because Noetherian, one of the equivalent definitions was there is no strictly ascending chain of ideals. Okay, so that's exactly this. So let me write. So I don't want to write everything. So right. So we iterate this process. Okay, it must stop. After a finite number of steps. Since otherwise, okay, would have, okay, an infinite strictly ascending chain of ideals of A, and this contradicts Noetherian. So this is the proof. I hope it's clear, right? It's not a difficult proof. I think it's not at all difficult, I think. Okay. Right. So, and then the second step, this is now the proof of this other step, this other lemma. That's a little bit, I think, a little bit tricky. I mean, not a bit less obvious. It says in an Noetherian ring, I need Noetherian. Every irreducible ideal is primary. Okay, and I think it should be clear these two lemmas together prove the theorem. Okay, now how is this proof? As I said, I think it's a little bit tricky. Okay, maybe the ideal should have a name A. Okay, so now I can save a little bit of notation. Without loss of generality, I can assume that my ideal is the zero ideal. I just replace, like I always do, I replace A by the factor ring. Okay, I can always do that. Okay, since I make a statement about any rings, I can do that. The factoring, of course, will also be Noetherian. So let's assume that 0 is irreducible. Question is, what does this mean? So the 0 ideal is irreducible. Okay, so good. I want to show the 0 ideal is primary. So I take a product of two elements, which is 0. Okay, let's say y is non-zero. And I have to show that x is nilpotent. I want to show that x is nilpotent. Okay, then because if I manage to do that, I've shown the 0 ideal is a primary ideal. I'm done. Okay. So now what do? We look, okay, we look at the sequence of annihilators of powers of x. So annihilator of x is contained in the annihilator of x squared and so forth. Okay. And now I can use that my ring, okay, because my ring is Noetherian. There is some n, and after that, this ascending chain of ideals becomes stationary. So the annihilator of x to the n will be equal to the annihilator of xn plus 1. Okay. Right. If xn plus 1 kills, okay. Okay. Right. Maybe I shouldn't say it. So we have this. Okay, and the claim, what is the claim? Right. Now I want to arrive at the decomposition of 0. And I claim I have the following decomposition of 0, x to the n, intersected with y. I claim that's the 0 ideal. Okay. You see, once I have shown that, I'm done. Okay. Okay, maybe I write this then, done. Okay. Namely, 0 irreducible and y not 0 implies that the x to the n must be the 0 ideal. Okay, because 0 is irreducible. Not both of these can be different from 0. Can be, yeah. So if this is not 0, then x to the n must be 0, and I have shown x to the n is nilpotent. So we need to prove of the claim. Okay. So how do we do that? So all of these proofs, somehow they are, I don't think they are very intuitive in a way. So let's, that's algebra. That's the devil of algebra. It's just abstract. Okay, so let's a little bit analyze. Let's say I have an A, which is in the ideal generated by Y. But then what I can say, AX, what can I say about AX? Now, A is a multiple of Y. So AX is a multiple of X times Y, but X times Y is 0. So I can have this. Since X times Y is 0. Okay, good. So now let's find out what can we say if A is in this principal ideal. Okay, so this means there is some B such that A equals B times X to the N by definition. But now comes the crucial thing somehow. Crucial. I know, okay, by this Noetherianity, these two annihilators are the same. So right, okay, maybe I was a little bit, no, it's good. Maybe this was too early. Maybe I moved this, maybe intermediate step. I think what I first want to say is if I multiply this with X, okay, right in the other order and have this, and this is 0. So I think I wanted to do this way. And then I see, okay, I was going too fast. Then I see B is in the annihilator of xn plus 1. But now I use the yellow thing here. Okay, this is now this, okay, having this property. Okay, so I see B times X to the N is 0, but B times X to the N, that's A. So A equals 0. So we have shown, right, have shown the claim. Okay, proof is done. Not a very intuitive proof, I'm sorry for that. But okay, but are there any questions on the details? Just the logic? Okay. Okay. Right. Good. So we have established the existence of the primary decomposition. Okay. So the next topic, and this is, I mean, for the end of the lecture, let's see to what extent is this unique. Okay. This is quite a subtle question. It's not easy. Okay, so study now. Uniqueness. To be honest with you, I don't fully understand this. I'm always worried. I mean, if it's about primary decomposition and so, that's a difficult matter. I mean, there are many, many subtleties. I don't really understand it well. Okay, good. So, the uniqueness. So I have another auxiliary result from, let me write it. So I even want to skip the proof for lack of time, but it's not a difficult thing. So if A is an Noetherian ring and A is an ideal, so the claim is there is some n integer, yeah, such that R, the radical, nth power of the radical is contained in A. So the point is this. You see, if you, for every individual element of the radical, take an x in the radical, then you find an exponent n depending on x. So that's x to the nx is in A. So this you know for every individual element of the radical. But the question is, can you find an exponent that is good for all elements? Okay. And without any further assumption, this is not possible. But this says, okay, now it's not really surprising. If the ring is Noetherian, then it's possible. Okay, you can find an exponent which is good for all elements of the radical. So I skipped the proof, I think, because I'm pretty sure otherwise I will run out of time. So I skip the proof. Okay, skip proof. Let's say proof as exercise. That's always an elegant solution. It's not proof as exercise. Okay, proof as exercise. Or you just read it in a TIA method. It's we will not learn a lot from this proof. Okay. So, and the corollary is this: is in an Noetherian ring, the nil radical is nilpotent. Okay, in an Noetherian ring, the nil radical. So, what was the nil radical? The nil radical is just the radical of the zero ideal. Okay, so it's nilpotent. Okay, because R of 0 to some n is in 0. Nil radical is nilpotent. Okay, good, good. Right, so, okay, before I go on, let me summarize a little bit what we know about primary ideals where the corresponding ideal is maximum. So I already said this is a situation that we understand relatively well. So maybe let me summarize this in this corollary. 716 is useful to have. So A is an Noetherian ring. Okay, M a maximal ideal. And Q is any ideal of A. Okay, now I have the following equivalent conditions. Okay, 3 conditions, they are equivalent, but okay, first one, what I want to characterize is Q is M primary. Okay, I want to understand this. Equivalent to it, actually we know it already, but it's good to summarize. Second is the radical of Q is M. Okay, so it's clear if Q is M primary, then by definition the radical of Q is M. On the other hand, we had a result saying if I have this, then I know this is maximal, then I know Q is primary. Okay, so we know this already. Maybe I put the reference in the proof. Third condition, it's useful to have, there is some n natural number such that I can sandwich Q between M to the n and the maximal ideal. Okay, so I think this is, so far I didn't write. This is the new condition. Okay, so somehow this is something, I think this is important. Maybe I put it in yellow. This is one way to think about M primary ideals. Okay, so it's an ideal, it's in M, it's somehow between M and some power of M. You know, when you take powers, you get smaller and smaller. This is the meaning, okay? Okay, as for the proof, there's actually not much to do. But, so what did I say? 1 to 2 was clear. 2 to 1, that was proposition 4.2, I explained already. Okay, 2 to 3. Let's see. Right. So now this requires this unproven proposition. I mean, the one 714 that I give you as an exercise. Okay, use proposition 714 because yeah. Yeah, that's yeah, I just apply this to M, okay? And M is the radical of Q. And 3 to 2. Okay. So I assume I'm in the situation of the yellow box. I have to show that Q is M primary. So then what I always do, okay, I have this inclusion. I take the radical. The radical of M to the M is M, is contained in the radical of Q, is contained in the radical of M, which is M, of course. I can write it. So I get equality. The radical of Q is M. Okay, and then I can say Q is primary by the proposition 4(2). Okay, and I'm done. Okay, now I'm like, okay. More space. Question? Okay. Right. So how do we proceed? Regard to uniqueness. Right. So there is a concept, it's the concept of the associated. So if you have an ideal in an Euclidean ring, an ideal A, then you can associate it with a finite number of prime ideals. So this is actually the modern viewpoint. It's closely related to the primary decomposition. Okay, and now I want to study this. Okay, so why is that? Let's remove this. Good. Okay, so what I will do now, okay, back to primary decomposition, okay. I have to think, how do I motivate what let me see, how do I want to explain it? Okay, so, okay, let's recall the notion of ideal quotient. Recall ideal quotient. So far, we used a lot this operation of taking radical. Now we take another operation. We will be important. This is the ideal quotient. A divided by X. Here is the definition. Corresponds of, okay, consists of those ring elements Y such that X, Y is in A. That's an ideal. It's the ideal quotient. Okay. You can also write it as an annihilator. Okay, why not? I can write it as the annihilator in the, okay, of X bar in the factor ring. Okay, annihilator. Annihilator of X bar in A module A divided by A. So this is just another way of saying the same thing. Okay, and right, so always, okay, of course, A is always contained in this. Okay, if you divide, you get something bigger. It's a bit strange, but that's how it is. Now, what we want to investigate this quotient when A is primary. Investigate Okay, the goal is investigate if A is primary. Okay, and it turns out in this situation, okay, we can understand this quite well what it is. This will be kind of key to the investigation. Okay, so before I go on, because I will use it several times, maybe let's rewrite. What does it mean, primary ID? Okay, so if Q is M primary. So one way to say was this, X, Y, maybe I need a little bit this, it's not good to have this white. So if I have a product two of element, X times Y is not in Q, and X, how did I say it? Yes, if X is not in Q, then Y must be in the radical of Q, and this is P. So we know this was the defining property. I just want to say, so it will, equivalently, I could also write it this way. If X times Y is not in Q, now I do the contraposition of this implication. Okay, I say is do I say okay? Okay, and say if Y is not in P, then X must be in Q. Okay, so it's okay. Okay, and what is the next? Okay, next level. I have time to write it. Let me write it. I feel I'm a bit rushing today, but maybe on Thursday we don't have to rush anymore. Okay, it's about these quotients. So let Q be M primary, X in A. Okay, and so I want to understand these quotients, Q divided by X. And I claim this is the whole ring if X is in Q. And okay, if X is not in P, okay, I will illustrate by a diagram, then this is Q. Okay, so maybe, okay, there will be a third point. So maybe to illustrate, maybe, okay, so what is the situation? I have Q in P, P is the radical, and this is in A. Okay, now, no, now you see, where do I pick my element X? If my element X is in Q, then the quotient is the everything. If, this is unreadable, if X is not in P, then I get Q. Okay, and this now I'm for the intermediate situation, if X is in P but not in Q, so this is the remaining situation discussed, then I cannot say exactly what will be the quotient, but what I can say for sure is that the quotient ideal is P primary. Okay, so hence the radical of it will be P. Okay, so like the upshot is this ideal quotient Q is P primary. You divide it by a point. If it's not everything, you always get a P primary ideal, always. And you see, I mean, that's the first statement. Okay, maybe I don't want to go over that. Okay, I don't go over time because I always start late. So I can do the proof. Like point 1, I say this is trivial. I mean, it's just abstract. Let's say X is in Q. Then 1 times X is X is in Q. So 1 is in this quotient ideal. So it's trivial. 1 is here. This is clear. Okay, so this is clear. Okay, so 2. Okay, 2. So y is the quotient Q. Let's check. Let's say y is in Q divided by X. Okay, this means XY is in Q. Okay, and then now in part 2, I assume X is not in P. So this is this assumption, X is not in P. So what I can say, therefore, because Q is a primary ideal, Y, okay, I should close this. Y is in the radical. Okay, what do I say? I'm messing up stuff. If X is not in P. Then I want to say Y is in Q, and I'm done. Right. So I have shown part 2. Okay, and I suggest maybe there's enough time. Maybe I prove the part 3 next time, and maybe I recall the whole lemma. So what we will, but maybe, So what we will do, okay, maybe the outline is this. This is what we will do is this. Okay, so if I have an ideal A, I want to associate it with certain prime ideals. So I look at these quotients, okay, and say they're radical. Okay. Now, if this is prime, okay, if prime, call P prime ideal associated with A. Okay, so this will be a definition. This will be a definition that we will study next time. Right. And what we will learn is what are these prime ideas associated with A. We will learn the following. You take A, do a primary decomposition, like Q1 up to QR, look at the corresponding radicals. Finally, many are those, finally many prime ideas, and these are exactly these prime ideals associated with the ideal. So this is like an alternative viewpoint for looking at this part of the primary decomposition. Okay, and then we get a finiteness theorem, and we get, okay, you can say something about uniqueness. Okay, that's the plan for the last session. Okay, maybe I stop the recording now.